this was the example that we were looking at, or we looked at that told you that the situation in the case of not having common support for finding minimal sufficiency is a little bit tricky. And then we ended up so stopping here at the empirical distribution. So this is sort of a very interesting object. The empirical distribution is very important. That's why I usually spend a little bit of time on it. So if you think about IID data from a model, the information in this data as far as, let's say, the information relevant to estimating theta in general is captured by this empirical measure, which is a probability measure or probability distribution on the same space. It's a discrete probability distribution, and it captures the information in the data. So it's a distribution of a random variable that takes value xi with probability 1 over n, and if some of them are repeated, so you get more probabilities. For example, in this case, we have that 0 is repeated 3 times, so effectively the weight would be 3 over 7. So more likely to observe that under this probability measure. So why this is important? The easiest way of saying it is it's sort of minimal, not minimal. It's sufficient in the case of IID data, right? So and maybe in the case of exchangeable data. So if you can exchange the order of x1 and up to xn, and the distribution doesn't change, then you don't need the order, or the order doesn't bring any information. And this keeps all the information except the order, if I'm not wrong. In the case of continuous distributions, this distributions of continuous with respect to the Lebesgue measure, all these points would be distinct. So effectively, all of them would have a 1 over n weight on them. And there are a lot more interesting properties of this. So this is sort of the non-parametric estimation of p theta, or like an estimator of p theta. And you can show that this converges to the true distribution. So just to point out that Pn will converge to p theta, assuming that x1 up to xn are coming from p theta. The convergence might be slow convergence, but if you define proper convergence of probability distributions in whatever metric you want to use, this in general holds, either in probability, almost sure, or whatever. So the thing is, this is converging to that, and so it's sort of a consistent estimator, as we'll see. This is called consistency, without using any information. Okay, so there is a consistent estimator of this, but why then we do all this stuff with parametric models? You can think about it. Okay, think about it for yourself. Why we want to impose a structure so this belongs to a family, if no matter what this probability distribution is, this is going to be always a consistent estimate. So I'm not going to prove this, but I just want to point out the interesting properties of this. Not only is sufficient, but as n grows, in the IID case, it would converge to the true distribution. Okay, sounds good. You should be able to prove simple versions of this. For example, Pn, if you apply it to a certain event, this should converge to probability of that event under this. So that would basically count how many x1 up to xn lie in set A divided by n. So it's like the proportion of the data points that land in set A that would converge to the true probability. So this is easy to show for any given event. So that should give you some idea why this is true. In any case, so this is like a side note. Side note, Pn is consistent for p theta. Good. For now, it's sufficient for us. the sufficiency is what matters. And this is like a little example that shows that basically, if you follow this argument, if you have a finite sample space, so X takes values in a finite alphabet, A1 up to AK, and then let's say the probability model is the collection of all probability distributions or measures P on X. So that's going to be my probability, this space. Then you can think of P being parameterized by a vector of size K, which is what that probability measure, the mass that it puts on these singleton events. So on each one of these alphabet spaces, it's like the letters of the alphabet, if you view them as an event. So this is very similar to what like you've seen in homework 1. So this you can think of this as a parameter that parameterizes the class of those probability measures, and then you want to estimate this parameter. You form the empirical measure, and you can see that empirical measure, there's a bijection to this frequency of observing each particular letter in the data. Okay, so if you think of this as the frequency of observing letter 1 among x1 up to xn, this is the frequency of observing letter k. And then because so empirical measure is sufficient, and this is sort of in bijection to that, this is going to be sufficient as well. And you can also argue that in this case, this is going to be minimal sufficient. I'll let you argue that for yourself. So that's a little bit of a side note, but final example on minimal sufficiency. Okay, questions? Yeah, we're going to skip this. There are some, let's say, formal statements. So this is from theory of point estimation. Basically, this is a formal statement of what we've seen before. If you have a dominated family with common support, and the family is finite, so this omega here has this form. There are like k plus 1 parameters. Then this guy, which is the vector of likelihood ratios, this is sufficient. So if you want to have a formal proof, or like formal, I don't think there's a proof maybe in the book, but if you want to have a formal statement, look at the theory of point estimation. This is one such example. We already sort of proved this. If you like fill in some of the details that I mentioned, this is what we proved. So then you might worry a little bit about when this is infinite. So when the parameter space is infinite, one way of dealing with this, if you want to be really precise, is this other proposition. So if you have a dominated family with continuous over common support, and if you have a subfamily here means there is a subset of parameters that you keep. So P is a collection of probability distributions, you keep a subset. And usually that would be a finite subset for you. But this is more general. So if you have a subfamily P naught, and then T, a particular statistic, is sufficient for P, and minimal sufficient for P naught, it has to be minimal sufficient for P as well. So you establish minimal sufficiency in the subfamily and sufficiency in the larger family. And then you have minimal sufficiency in the larger family. So I'll let you think about this. This is not really that difficult to show. The only thing that you have to worry a little bit about this part, that almost everywhere with respect to P naught implies almost everywhere with respect to P, which is sort of the tautology because P is larger, and then you can write down the statement. So just remember what the minimal sufficiency is, and you can easily prove this. It's like a few lines of proof. Once you convince yourself of this fact, if you really want to be precise. So this is the sort of proof. I'll let you think about it, but it's sort of intuitive if you think about it. So that gives you one strategy if you want to formally prove something is minimal sufficient. You don't have to do it. I mean, I like the likelihood approach that I mentioned, and usually that's good enough for us. And I would be okay if you argue it like that, write down the likelihood function, establish a bijection between the likelihood function. But this is like another way. So suppose you have a normal family. We already showed via the likelihood approach that the summation, for example, of xi's is minimal sufficient. But if you want to use this proposition, you'd pick a subfamily. Let's say it's just enough in this case to have a 2-point family, theta naught and theta 1. We conjecture that this is minimal sufficient. We know actually, but let's pretend that we don't know. We know that it's sufficient by factorization theorem for the larger family. So you know that this is sufficient for P, which is just the class of all normal theta 1, theta in R. So sufficient for a larger family by factorization theorem. And according to that result, if I can show that this is minimal sufficient for this smaller family, then I'm done. And for this result, or for this claim, we can use this result because it's a finite family that we picked. I can just form the likelihood ratio. This is everything has common support. So the likelihood ratio only has one element because there are two elements. I take the likelihood ratio between, let's say, or this one relative to that. And I can also take the log because log is, again, monotone, like bijective, as we discussed. So, okay, so you form this likelihood ratio and then the log, and then you simplify, you end up with this expression. And then the claim here is that T of X is in bijection to this log likelihood ratio. And so it has to be minimal sufficient for this 2-point family. And because T is also sufficient for the larger family, it's going to be minimal sufficient for the larger family. Okay. So why is it a bijection? Let's see.
Because T of X is already, the sum is already minimal sufficient. And so since the log likelihood is just a function of an already minimal sufficient statistic.
No, actually, it's the other way around.
Oh, the other way.
We are trying to show that T of X is minimal sufficient.
Oh, okay.
Right. So you're using the fact that the log of L is itself, this is minimal sufficient. And you're saying that this is in bijection to that, so it's minimal sufficient. So by why this relation is like a bijection?
Because log's monotone.
Yeah, log is monotone. So that's saying that the log of L theta is so L theta 1 of X is in bijection to log L theta 1 of X. That's fine. So we know that this is minimal sufficient. So this has to be minimal sufficient. Now I'm saying I have written this as a function of this. So this function of T of X is monotone. Sorry, like bijection, yes.
It's just an affine function.
It's an affine function, yes. And then it's going to be a bijection if these are not the same. So this has to be non-zero. Sorry, not equal, which is implicitly we assume. Otherwise, it would be 1-point family. So you can't do it with 1-point family. You need two different thetas. But if assuming so, with theta not equal theta 1, then this is a affine function, a linear function if you want, but some constant. So it's invertible. Good. Okay, this is for people that want to use formal results, or you can use Keener's if you believe Keener's result is formal enough. Okay, now I'm going to move on to something else. So any questions about minimal sufficiency? So now we're going to move in the same direction. So let me show you an example that shows that maybe there's something even more interesting than minimal sufficiency. So sort of minimal sufficiency captures the maximum compression in a sense. But something interesting happens that this suggests that maybe that's not. So maximizes compression in the sense that we made, like made clear or made precise that like if I have another sufficient statistic, there has to be a function that maps it down to minimal sufficiency. But there's something else going on. And so this is the idea of completeness. So to get there, let's introduce this idea of ancillarity or an ancillary statistic. So we have a statistic, and this is just a function of the data, hence the statistic. That's the definition. And it's called ancillary if the distribution does not depend on theta. Okay, so I have X, whose distribution in general depends on theta. And then I can form a function of it, let's say, whose distribution does not depend on theta. Intuitively, this does not carry any information for parameter estimation. So statistically, it's not useful. An example is if you have a location family, remember location families, right? Xi is like F, let's say X minus theta, that's sort of the density, carried from 1 to n. So I draw from this family in which the parameter is the location of something. And then if you form like the pairwise differences or the difference that's of xi to the jth order statistic or difference between order statistics or order statistic minus the mean or xi minus the mean, all of these would be ancillary. The reason is that you can write down this model as an additive noise model. So you can write xi as theta plus epsilon I, where epsilon is distributed like f. These are IID. So this f is this baseline. For example, if you have xi's are from like normal theta 1, that's an example of this location family. Then I can write xi as theta plus epsilon I, where epsilon i's are normal. It means 0 and 1. So this doesn't have anything to do with theta anymore. And the reason why you can do this should be clear if you know how the distributions or densities behave under transformations, right? Do people know what happens to the distribution of a random variable when I apply a transformation? Have people seen this before? Suppose I have a distribution like X. This is like basic probability. So X has a certain, let's say, density. What is the density of X plus 2? Sorry?
So they just add still, but
F. So for example, F could be the normal distribution, right? 1 over root 2 pi e to the negative x2 over 2. So then if you say that x plus 2, so this guy is going to be centered around 0. This guy is going to be centered around 2, so it can't have the same distribution, right? I'm going to write it as f of x, for example. And so imagine that this is a function. So what I really mean is the function that maps x to f of x. So if this is the density of x, what is the density of x plus 2? Let's say I have a general like g of, okay, let's say I have a general function g of x. Let's say g is monotone. 1-to-1, basically. The 1-to-1 corresponding to bijection. Can I figure out smooth and so on, bijection? Smooth, their derivatives and so on. Do people remember what the
Something like f of g inverse times the derivative of the absolute value.
f of g inverse times
But the absolute value of the derivative. And the
Yes, so that's
Determinate if it's, yeah, the, multivariate.
good. Yeah, you know what, yeah. So that's basically the rule of transformation. So if you want to remember, so maybe teach a useful thing, because you're gonna forget about completeness after like this course, but this is useful. So so if I have x maps to g of x, I have a distribution on in here. So it's like distributions are like masses scattered around. So you want to see how this transfers to the other part. Like, so if you have distribution on x, then g of x without a distribution, it's like a redistribution of the mass in some way. How do we determine that? So you'd say, okay, I'm here, right? There's this piece of mass that I have here, which is like f of x. I should do maybe p, because that's f and g are not good notation. So this is p of x. That's my probability. Okay, so if I have a little tiny interval around x, the mass that I have there is this, right? And this d of x, so this is d of x around x, basically. Sorry, I need more room. I have to maybe make it bigger. Do this. Add a page somewhere. Okay, let's move this down. Make it big. Okay, so it's like I have x and then x plus dx, right? And then there is like a slope here, which is like g prime of x. This is like, imagine that around this x, if you have a very tiny interval, it looks like a linear function. So basically you have to determine what happens under linear transformations. So this length is gonna move to like what here? So if I have a length dx or delta x, what would be the length of this interval? Yeah, it's just everything is univariate, right? So this is roughly like, if you want dy dx, right? Basic. So dy would be roughly g prime x dx, right? And dx could be like positive, negative. I'm gonna put like an absolute value here to make it positive. So the length of this dx, it could be like dx is negative. So it would be like negative dx and x here. So I don't care about the direction. So this mass corresponds to the mass there. So whatever the distribution is, so let's call this y, is g of x, right? Py of y times this d of y has to be like roughly or equal, basically, p of x, d of x. So that's the probability doesn't change. So the fact that x, for example, belongs to this interval is like y belongs to that interval. Okay, so like the probability that x belongs to, let me do this, x plus dx. X and x plus dx is the same as the probability that y belongs to y and y plus dy. Okay, this is that probability, this is this probability. And then you rearrange, you get py should be equal to dx over dy, dxx. Okay, and this is like 1 over like inverse function theorem or whatever. Dxx, in any case, that would be it, something like that. And then this is going to be g prime of x. You haven't done any mistakes, so that would be p of x, and then x is like g inverse of y. So you proved your result if you haven't made any mistakes. Okay, so it's just you have to figure out what so probabilities are the same, and then the probabilities in terms of the densities would look like this, and just you have to figure out how the length here would transfer to the length there. And so now if I have a transformation, which is g of x is x, let's say plus, well, let's say x minus theta, right? That would be my y, or x plus theta. Then g prime of x. What is g prime of x? 1. So whether we did this correctly, like, or the inverse, it doesn't matter because 1. So we get x is like g inverse y. What is g inverse y? Well, so py of y would be px y minus theta, right? Correct. So if p of x was f of x, then y would have the density y minus theta, which is what I want. It's like that location family. So this transformation would do this to the density. So shifting the density would be like adding like a constant. So how many people like this is completely new or okay? Just a reminder, right? Okay, so that's what it is. So this is the this guy, and then I can write it like that additive model. So then can you tell me, so this hopefully is clear to people. So if I have something like that, epsilon is f, then I have that location family. So what happens now? Why these are ancillary?
One and two epsilon share theta, right? So you subtract.
They share theta, yes. So when you subtract, you just get like epsilon I minus epsilon j, which has nothing to do with that theta. The same goes for the order statistics, because when you order them, the theta is going to come out. So ordering this would be like ordering epsilon. So also taking the average would take theta out. And so if you center the variables, take the pairwise differences, all of these are ancillary statistics, okay? So they're useless for estimating theta. Right? If you have location family, once you subtract the mean from every data point, let's say, you lose all the information. Basically, the information is in the center. So now this causes some sort of a trouble because, let's say in the Laplace family, we saw that the order statistic is minimal sufficient, right? If you think of minimal sufficiency as the maximal compression, so this has all the information that you need, but then I can form these functions of it. So there are these functions, although I have a minimal sufficient statistic. For example, I form this function of it to take the first element and the last element of the order statistic. I form a function. This doesn't have any information. So there are functions of my minimal sufficient statistic that don't carry information. You might be okay with this. It's fine. So this is, you're not saying, we didn't say that all the functions that you form of it have to have information. But the statisticians sort of figured out that there are cases in which you have a minimal sufficient statistic such that no non-trivial function of it is ancillary. And those are called complete statistics. So there is a situation, so this situation is like there is a defect here, which some other models don't have. So to reiterate, you have a minimal sufficient statistic, you can form functions of it which are non-trivial, that don't carry any information. It's fine so far. But there are also situations in which you have a minimal sufficient statistic such that no non-trivial function of it produces an ancillary statistic. Those are the interesting cases that this completeness tries to get to. I'm going to give you the definition before doing that. There's a weaker notion of ancillarity, which is first order ancillarity, which is just saying that the mean or the expectation does not depend on theta. So if you have a statistic, just give me a second. If you have a statistic whose mean doesn't depend on theta, it's first order ancillary. Maybe higher order moments depend on theta. But if something is, so this is also first order ancillary, right? All these are first order ancillary. Yes.
Just what you said. Is there a way to characterize the models by how much ancillary they have?
That's sort of this.
Zero or but like a lot.
How much ancillary? So that's the difficulty. The model. So this completeness is trying to capture is there a statistic that doesn't have like this ancillary information in a sense, okay? But whether a model has ancillary information, I don't know if there is a way of saying it, but I can give you an example now, like a definition of completeness. This characterizes this situation to some extent, yes.
But when you say contains ancillary information, does that mean it like depends on data in some way?
That's not a precise, this is the precise statement. So if you want, this is the statement. So this is this notion of completeness, which is stronger than minimal sufficiency. So a statistic, this like first has nothing to do with minimal sufficiency. Forget about minimal sufficiency. If the statistic is complete if this conditional statement holds. So whenever I form a function f of t and I take the expectation under theta, under the model, if this is constant as a function of theta, then f of t has to be constant. So f of t has to be like the trivial function. So for all constant functions, this is going to be definitely true, right? But completeness says that these are the only functions that are first order ancillary.
Yeah, so I'm confused on the statement about that. So is completeness saying that we do contain ancillary information?
So this statement contain ancillary information. Maybe I shouldn't mention that. So what do you mean by contain ancillary information?
Yeah, like for your example where the Laplace location family,
Yes.
that difference of order statistics contained ancillary information.
If contains ancillary information means that there is a non-trivial, non-constant function of it that is ancillary. Yes, then
Okay.
it is like that, and so it's not complete by this definition. So if you look at the contrapositive, so this is saying if this is not constant for all t, then expectation of f of t is not constant. So if you pick, this is equivalent logically. So if you take a non-constant function, then once you take the expectation of that new statistic, it's not going to be a constant as a function of theta. Or let's say, I should say, yeah, so not equal C is equivalent to saying that it's not constant. So this contrapositive says, if T is complete, no non-constant function is first order ancillary. Okay, because it's not first order ancillary, it can't be also ancillary, because ancillary statistics are also first order ancillary. Yes.
It's like these notions of ancillary and completeness are like definitions on the basic statistics and not like
Yes.
the model, right?
Yes.
And the function of the statistics alone.
Yes, but because they talk about like, so minimal sufficiency is sort of tied to the model.
Yeah.
So it's not, and then this completeness also like tied to the model. So it tells you something about the parametric family of the models that you have, like the model itself, but it's a property of statistics. It's like indirect way of looking at the models. Right, we saw, for example, the two different models that we had, Gaussian location family and Laplace location family, the minimal sufficiency was different for them. So the minimal sufficiency sort of told you something about the nature of the family. This is similar, but that's how you deal with like information in the family. Okay, so so the first, that's the definition. It takes a while to maybe get used to it because it doesn't, it's a conditional statement. It's not saying that the first, like this is true, okay, or this is true. This is saying if this is true, then this has to be true. So you have to think a little bit about it. But intuitively, what it says is that I can find a non-constant, if you want to say non-trivial. Non-trivial is ambiguous, but it's easier to say that non-constant. If I find a non-trivial genuine function, let's say, of this statistic, such that it's first order ancillary, then it's not going to be complete. So here's the example. So you had the Laplace family, this is ancillary, and this can be written as a function of these. Just take the function to be the function that takes the n tuple and then subtract, let's say, the first from the last. So that function is definitely not constant. So this constant again is almost everywhere p. So under the family is not almost everywhere constant. The Laplace family sort of puts all the mass over the entire real line. So this is definitely not constant almost everywhere in the family. But if you apply it to the statistic of the order statistic produced as ancillary, the statistic, so this is the order statistic here is not, so x1 dot xn is not complete in the Laplace family, although it's minimal sufficient, as you've seen. So this gives you a counter example, or like shows that minimal sufficient statistics need not be complete. Okay. Yes.
Can I ask a question about notation?
Yes.
If you scroll up when it said like xi minus xj, but then and then x like the j's in parentheses.
Oh yeah. So this is the order statistic notation, if you remember.
Oh right. Okay.
Right. X1 less than or equal to. So this is the jth largest, basically. Okay. X1 is the like the smallest, basically. X2 is the second, the jth smallest, probably we have to say. Yeah, x1 is the smallest, x2 is the second most small, or smallest. X3 is the jth smallest. Xn is the nth smallest, which is the largest. So these are order statistic notation. Thank you for that clarification. Yes.
Could we get some intuition on why this idea of completeness is useful? Like, are we saying that it contains even less information than the minimal sufficient?
It captures sort of like more the compressed like notion of information. It's such compressed that you can't squeeze any more out of it. Right? There is no way that you can form a function of it that it's even ancillary. Okay. So any sort of non-constant function has some information. It's like this ball of information that's like so dense that whatever you do to it, there is a bit of information about theta that just spills out. Okay. It doesn't say that once you form a function, that will be sufficient, but it says that it carries some information still. You can't like lose information. Yeah.
Potentially very dumb question. So is an ancillary statistic good or bad?
Very good question. So is ancillary good? Depends on what you want to do.
Okay.
Yeah. What do you guys think? Is ancillary good or bad? Bad. If you're a statistician, it's bad. If you like are in like garbage disposal, data garbage, this is good. So like this is like you destroy the information. So if you try to destroy, someone gave you like private information, you're trying to destroy the data like information. This is the best way of doing it because you lose the information completely. If you want to recover the information, this is bad. So as like most things, it depends what your intentions are.
So that's why we're going for a complete statistic, so that if we make a non-trivial function of that statistic, we still have the information.
Yes, so this is saying this is so informative that no matter what you do to it, like bar forming a constant function of it, which obviously doesn't, whatever you do to it, like reasonable thing to do, there is like a little bit of information about theta that remains. There's a very like strong notion of information. Yes.
Does that mean like a non-complete statistic cannot always be like a single statistic? For example, if you have like a single ordered statistic is already been like sufficient.
No, the function that I'm saying, like mentioning here, it doesn't necessarily have to be multivariate. So you can form like, if I have like x1, I can form like the function like x1 squared. So remember, this is like what I'm talking about is like, this is itself a function of the entire data. So I can find for other functions of the data out of it.
Even the x1 squared sometimes can be non-complete.
Yeah, but what I'm saying is that completeness and non-complete doesn't mean that there's like a single coordinate, if that was your question, right?
Yeah, I think because you have a vector of like all the statistics and you do some operation that non-trivial operation, non-trivial function operation, you cancel out some information because of you have multiple things. But if you only have one thing there, then no matter how except the constant function, then you can do some operations that you still cannot lose information for that. For that thing, then it has to be a complete.
Right, but what I'm trying to mention is like, or get to, is that the fact that things are multivariate doesn't come into play here. So
Okay.
there's no reason why, like, if you have just a like x1 or like maybe the sum, this is still a function of the like the original. Even if you have a single observation, you can still talk about completeness. The loss of information is not combining some of the coordinates. That's one possible function, right? There are other, like the functions are more general, right? So you could do, yeah, so this is more general than, yeah. Here, like this was a simple example that you could like manipulate these coordinates because they share some mean, you can subtract. This is easy, like when you're doing it, but the idea is general. Okay. Like, good, yeah.
So I guess going off of that, are you implicitly constraining F to only be real value? Because if you allowed it to be vector value, then you could just do silly stuff like have a two-component function that's the same on each component, and then follow that by subtracting, and everything will fail to be complete.
So can you give me the example that you
Yeah,
can think?
So like if you're allowing F to be vector value,
Okay.
just scalar value, then you could just have like F be the thing that sends like from R2, say that sends T to T comma T.
To
You could
T.
follow this by like subtracting components.
Right, but that the composition of two functions would be my statistic, right? So you have to give me one function of T such that this holds. Right. You can try, but I think it would work still.
So does this work if you allow it to be vector value?
I guess so. Yeah, there's no reason why this has to be even in RD. It's a good point. So I'm not specifying the range, and I don't think it's necessary. But if you found a counterexample, let me know. It could be like mapping to an abstract space. Right, you can encode however you want. It's just that it's not constant. That's at least you have to be able to calculate the expectation. So if it's like too abstract, then the question is what the expectation is, but RD would be fine. Yeah, interesting questions come up once you start thinking about these problems. But okay, any other questions? Yes.
Yeah, I guess actually for that example, I guess it's not so much the issue with the range, but the issue with the specifying the domain of F, right? Because if T maps into a subset of the domain of F, this situation like that difference is not
That's
it's
fine.
not a constant function, but it's constant on the image of T.
So it has to be constant almost everywhere. That's the part that this tries to capture. So, so let's say almost everywhere. So for simplicity, let's do, there is a,
I think that's extent. Yeah, because you like push forward the measure on your T.
Yes.
And the measure would only be supported on that.
yes, exactly. So the family, so like this would have like a parity family decision, just push forward the original measures. And under those measures, this function has to be non-constant. Okay. No problem. I'll let you think about this. This is not an obvious kind of definition. But let's give you an example. Let me give you an example. Showing completeness is in general not easy. You're going to do it in your homework problems anyway for a couple. So there's some strategy, but this gives you an idea of how you could do it and what is required. So we'll see a general result for exponential families. I'm not going to prove it, but there's a general result that tells you in exponential families, the sufficient statistic is complete under certain assumptions. That's very useful for us. Here's another example. This is not going to be an exponential family, as we'll see, but it's easy to do, sort of. So x1 up to xn are IID from this uniform 0 to theta. If you remember, this was one of our examples. This is an example that doesn't have common support. It's like one of the examples that we'll work with. It's like counter examples to some settings. So we'll show that this maximum is complete. And you in your homework problems, you probably have shown that it's sufficient. Actually, we proved that it's sufficient, I think, by factorization theorem. We proved that it's sufficient. Here we're going to prove that it's complete. We'll see a result that these two imply that it has to be minimal sufficient as well. So to show that this is complete, I have to, so one strategy is to start from, so let me tell you the strategy. So to show completeness, one strategy is to start with a generic function. So remember, we have our t is like known to us. If you want to say t of x. So we know this statistic, but we take a generic function of t and then set this equal to a constant for all t, for all theta. And without loss of generality, I can take this constant to be 0. Let's say f is real valued. Going back to our discussion, let's say f is take a real value function, and or it could be like r to the d if you want, but for now it's like real valued is enough. I think most likely in the definition you can assume that f is real value. That would be enough for our case, or at least you can define it that way. I can take c to be 0 in the definition, it doesn't matter. Can you see why without loss of generality I can assume that c in this definition is 0? If I show it for c equal to 0, then I have it for all c. Right?
You could just define a new function, g of t be f of t minus c.
Great. So you define a new function, which is g of t equal f of t minus c. And if this results for g with 0 on the other side, if you write it down, you get back this because the constants come out of expectations, right? So without loss of generality, we can do this with 0. So I'm going to do 0 here. And then you write down, this is an integral. Okay. You write it down for all theta, this would give you an integral equation. Okay. And then you have to solve that integral equation, show that the unique solution is sort of 0. Okay. And you can turn it into like a differential equation. So it ends up being solving a differential equation or an integral equation. So this is what happens here, for example. For example, if I want to write this expectation, I can do integral of f of t and then p theta. I'm going to write it as p theta of t dt here. This is the density of t under the model. Okay, bad notation, but if you want, you can like put a tilde here. This is not the original density of x's. This is for t. So this would be equal to 0. So you can see now that this holds for all theta. This gives you a lot of equations that have to hold for f. Then you want to prove that f is 0. System of integral equations. So what is the density of t? So how can I compute the density of T, assuming that x1 up to xn are uniform? 0 to theta. I guess you guys have computed something like this in your whole problems. Okay. How do we calculate the density of T of x? Yes, the CDF. So a CDF of T, let's say, I should probably do T theta. Yeah, I'm going to do this. It's hard to write it. FT T would be the probability that T is bigger than T or less than T. Okay, that's the CDF, which is the probability that the maximum of x1 up to xn are less than T. So what happens here? Sorry. Yeah, so before doing the product, like one more step maybe. Right, this is saying maximum is less than T, is like all of them have to be less than T. So it's like intersection of these events that xi is less than T. So it's the intersection of all these events, and these are independent, so you get product I from 1 to n. Probability that xi is less than or equal to T. So what is this? One over theta. So assuming that
T of the thing.
T over theta, yeah. So this is density is 1 over theta, and then you go from 0 to T. Okay. So you integrate, it's going T over theta. So you get T over theta to the n, assuming that T is in 0 to theta. Okay, above, what happens above theta if T is bigger than theta? It's just 1. Below 0 it would be 0, right? So it's something like 0, and up to theta it goes like this, and then it's going to be 1. So now how can I get the density? Sorry?
Just take the derivative.
Derivative, yeah. So this is going to be, how do I take the derivative? You guys know better how to do the derivative. 1 over theta n comes out, you get n Tn minus 1. Right, is that correct? Yeah, let's see if that's correct. Yeah, correct. Then I'm going to plug it in here. So I get integral 0 to theta, n over theta n comes out, f t Tn minus 1 dt, for 0 for all theta. Right, that would be my integral equation. Right, let's say theta bigger than 0. That's our parameter space. Okay. So that's this, again, this conditional statement. So I'm going to assume that this holds, then I'm going to show that f is 0. So if this holds, then this should hold. So we can drop this because theta is positive. If this holds, then that holds, and if that holds, then this holds. So I'm going to just drop it. I get integral 0 to theta f t for all theta bigger than 0. So this integral equation, can I conclude that f of t is 0 for all t or almost all t?
Do induction on the end and see that, integrate by parts and get that.
Induction. So let's say n is 1. Can you conclude that? No? Yeah.
That is, area is 0. Area can be 0 on your above tail 0 because that is tails positive.
So this is, you're saying this is 0, like the integral is 0, then it has to be 0. So let's say I have,
Is positive.
okay, so you're saying this is positive. So this is positive, then it has to be 0 where?
Above there has to be uniform.
0. Okay, so you're saying has to be 0. So this is a positive function. So why is it positive? Do we know?
Because stays from 0 to.
But do we know that this is positive?
It's any general function.
A general function, yeah. So I could have something like this, like symmetric maybe, around like. Was close. But there is a way of doing it though, so you can split the function into 2 pieces, positive and negative, and then try to argue that. That would most likely work. But yeah, what was that? Yes, that's not a bad solution, but yeah, we have to be more careful. Yeah, so you can take the derivative. What happens?
Just get the integral down.
Why? Yeah, fundamental theorem of calculus. The derivative of this I can take, because this is an identity, I can differentiate both sides. The derivative of that side would be f theta n minus 1. So you just evaluate the integer. So that's like fundamental theorem of calculus, or like Lebesgue differentiation theorem that came up very early on. This has to be 0 for all theta bigger than 0. This is positive, so this is implying that f theta is 0. So this doesn't have to be for all theta. So for almost all theta, with respect to the Lebesgue measure, but almost all theta, that's what we want. Okay. So you see some like heavy duty tools have to be used to show it. The idea that the integral is positive, so you could try to split this into the positive and negative part. Then you move, positive is like where the function is positive, negative is when you move it to the other side, to this side, and then you have to do a little bit argument. So if f is positive, for example, then your argument would imply. If it's negative, would imply that what happens if it has positive and negative parts, you have to use something else. Yeah.
Why are we integrating from 0 to theta? Don't we care about what happens after theta for the debate?
Derivative is 0. So this is like that, and then 0. So if you want to be precise, this is like this, and then 0 if theta does not belong to 0 to theta. So I'm taking the integral everywhere that there's mass, because the CDF is like this, 0 and then 1 here. So if you differentiate, but there's no mass on that's the density of theta, density of T. Are we good? Yes.
I'm not too sure about the fundamental theorem of calculus.
So what is fundamental theorem of calculus? Is that
It's like you can
anyone wants to like remind us what the fundamental theorem of calculus is? It is fundamental though.
Yeah, it's precisely that's there, right? Yeah, you can go from 0 to x of f t dt of that. You know, integrate as a function itself, yeah, as capital F of t.
Say a from this to t, right? Then if you have a like a integral, like integrate the function from a certain point up to, let's say, t, and then the derivative of this, no, the derivative would be just integrand evaluated at t. Not at all points, but at almost every point. But this came up whether that would be all points or not. Like an upgrade of this is called the Lebesgue differentiation theorem, if you want to see. But yeah, that's right. Okay, yes.
So I thought we had to show that f of t is a constant everywhere, and this is f of theta, is there no problem there?
So the function is that this is a dummy variable. You're trying to show that the function, so you can just call it
Okay, so
t
think
or
of that.
yeah. What you're saying is that this is identically zero. That's sort of what we want to show.
Okay.
The argument is just a name. Good. Any other questions? Yes. Maybe that was first. So, yeah. What was your name, by the way?
Michael,
Michael. Okay.
I don't think that's like super relevant, so maybe it's not like important, maybe we should talk to you. But like, it wasn't until you shifted it to zero, like in one of the boxes, like, I've never done any functional analysis, but to me, it looks like any function of t is orthogonal to its density.
Sorry, where did I show? I
That
didn't.
first box, right, like actually the blue box right there, so like, if
This
you think of
one?
that as like being an inner product, right, like the integral ft times its density,
Yes.
and being equal to zero, isn't that like, isn't that like an inner product? So like any function of t then is, any function of t is orthogonal to its density, is there any, I don't know, am I making that up?
That's a good point. Actually, we're going to talk about this exact inner product, sort of similar to this in the next slide. But
Like, is there any, like, I don't know, viewing these complete statistics from, like, I don't know, like this functional analysis perspective that you're doing, like,
that would be perfect. Yes, if you can do that, let me know. Yes, I think what Michael is suggesting, which I really like, if it's possible to do, is so there is this. It's actually very relevant because I want to talk about this in a different context. So if you have two functions, let's say on the reals, the big integrable, whatever. So if you take the integral of these against each other, this you can think of as an inner product, right? Yeah, are you trying to answer this or?
Yeah.
Okay.
Yeah, so I mean, you've described a particular subspace of functions that not every function has. It's the ones that integrate to zero when you like precompose them by the same. Right, so you're saying that like the density is orthogonal to that subspace. Yeah, so it's not every function, it's that particular subspace.
It's not saying that the density is orthogonal, it's just the function is orthogonal to these densities.
Yeah, like
Right.
the function in that class would be orthogonal.
Yeah, or like the densities have the property that they integrate to zero against everything that like integrates to zero just.
So there is this inner product, which is called the L2 inner product. Like you can think of the space of functions, you can think of functions as vectors, basically, right? So if you think of usual vectors, if these were vectors, I could define an inner product like this, I from 1 to whatever d, right? That would be the inner product between two vectors. This is similar, like integrating looks like an inner product. So you can think of this, the functional analysis viewpoint is that the entire function is a single point in some space, vector space. And then this is the inner product. And then you can like pretend that you're working with vectors now instead of functions. You like whatever you like projection or whatever you do in the vector spaces or you feed in the spaces, sort of you can generalize. And what Michael is suggesting is that this thing that we wrote here, ft p, let's say t tilde t dt, this is indeed like f p tilde theta L2, and this holds for all theta. Okay, and so it seems like, so if you believe that this is an inner product, or you can think of it as an inner product, then what I'm trying to say, what we are saying is that this is inner product is zero. Okay, this inner product is zero for all theta. Another way of saying it is that this inner product with some g, or sorry, yeah. So what can I say? Inner product with let's say, so think of a space of these densities, okay? The space of all possible densities from this model. So what you're saying is that this f is sort of if you project it, there's no component here. So the f is sort of orthogonal. And if you're orthogonal to enough things, then you just have to be 0. So for example, in RD, so if f, for example, is orthogonal to the first basis vector, the second basis vector up to the d basis vector, so these are like vectors, right? 0. So if there are enough things that you're orthogonal to, then f can't be. So this is saying the first component is 0, the second component is 0, and so on. So this f has to be in the end. So if you gather enough vectors and you're orthogonal to enough things, then you have to be 0. This is like the one functional analysis view, which I really like. But the issue is that this whatever space is not clear, right? So it has the property that they sum to 1. So it's like, so this is true, like inner product with 1 is 1, right? So this is like a linear constraint, right? And they're also non-negative and non-negative, I'm not sure we can use, but still like the fact that like they occupy a space depends on what kind of family you have. What kind of the completeness sort of is like this is enough. Once you're orthogonal to this, then you have to be 0, like sufficiently rich, sort of. Yes.
I guess it's saying that they span against something else. It's all the one against something else. The closure of their span is all else. Or else there'd be an orthogonal complement.
We are out of time, but this is an interesting discussion. So a span of what? A span of these?
Like the densities should span us, like this condition means that the densities span a subspace whose closure is all.
Yeah, so the span is dense in something. So is it like L2 or something like that? So let's say if yes, it's L2. So if the span is dense in L2, then it's true. Yes. So all of this assumes that things are in L2. So this is like has the second moments. So you have to worry a little bit about this, but if you're willing to work with L2, then and if these densities are indeed in L2, so you have to verify that is it true that, for example, this squared is finite? If the densities are in L2, then you can work in L2 inner product, stuff like that. But I like this viewpoint a lot. We can think about it, let me know. But it went like a very interesting direction. So we'll come back next time. You can read the next. So we're going to talk about this inner product and stuff related to this. Thank you guys.